Picture this. You pour yourself a cold drink on a hot day, drop in a few ice cubes, and watch them bob on the surface. Nothing unusual, right? Completely normal. Except, here's the thing, it's not normal at all. In fact, ice floating on water is one of the weirdest, most rule-breaking behaviors in all of chemistry. And if it didn't happen, life as we know it wouldn't exist. I'm serious, that innocent ice cube defying gravity in your glass. It's basically performing a physics miracle. And today, we're diving deep into why ice floats. Before we get started, check out the link in the description to download our ebook, What Makes It So Bizarre, and how this one strange property literally saved every ecosystem on the planet. So let's start with a question. Why does ice float in the first place? Okay, think about almost any substance you know. When you freeze it, when you take away its heat and lock it into a solid state, it gets denser. It packs together more tightly. That's why a frozen stick of butter sinks in melted butter. It's why solid wax sinks in liquid wax. It's the rule. Solids are denser than their liquid forms, so they sink. Water laughs at that rule. Ice is less dense than liquid water, and that's bizarre. That's not how matter is supposed to behave. Most materials contract when they freeze. Their molecules huddle closer together, becoming heavier per unit of volume. Water does the opposite. It expands. Ice takes up about 9% more space than the same mass of liquid water, which means ice is lighter, which means it floats. But why? What is it about water that makes it such a rebel? To understand this, we need to zoom in, way in, down to the molecular level. Let's talk about what water actually is. You already know the formula. H2O, 2 hydrogen atoms bonded to 1 oxygen atom. Simple enough, but the shape matters. Water isn't a straight line. It's bent, like a boomerang, with the oxygen atom at the center and the 2 hydrogens sticking out at an angle of about 104 degrees. Now here's where it gets interesting. Oxygen is a bit of a bully. It's more electronegative than hydrogen, which is a fancy way of saying it hogs the electrons. This creates a slight negative charge near the oxygen atom and a slight positive charge near the hydrogen atoms. Water is a polar molecule. It's got a positive end and a negative end, like a tiny magnet. And what do magnets do? They attract each other. This attraction between water molecules is called hydrogen bonding. The positive hydrogen of one molecule is drawn to the negative oxygen of another. These bonds are constantly forming and breaking, billions of times per second, as water molecules tumble and slide past each other. In liquid water, molecules are close together but still moving freely. They're energetic, they jostle, they form hydrogen bonds and break them just as fast. The structure is loose, flexible, dynamic, but when water freezes, everything changes. As the temperature drops, the molecules slow down. They lose energy, and those hydrogen bonds, they stop breaking so easily. They lock in, and when they lock in, they force the water molecules into a very specific geometric structure. A crystalline lattice, a hexagonal pattern with lots of open space. Think of it like this. Imagine a crowded dance floor where everyone's moving freely, bumping into each other. That's liquid water. Now imagine the music stops and everyone freezes in place with their arms outstretched, locked in a choreographed formation. Suddenly, there are gaps between people, empty space. That's ice. Ice is actually more organized than liquid water, but it's also more spread out. The rigid hydrogen bonds hold the molecules in a structure that's less compact, and that's why ice is less dense. That's why it floats. Let's pause and appreciate just how weird this is. In almost every other substance, freezing means compacting. Molecules get squeezed together. Density goes up. But water does the exact opposite because of hydrogen bonding. It's an anomaly, a glitch in the matrix of chemistry. Silicon does this too, by the way, and a handful of other substances. But water is by far the most important one, because water is everywhere. It covers 71% of Earth's surface. It's in the air, in the ground, in every living cell. And this one strange behavior, this density inversion, has shaped the entire history of life on this planet. So let's talk about what would happen if ice didn't float. If ice behaved like a normal solid and sank to the bottom, imagine a lake in winter. The air temperature drops below freezing. If ice were denser than water, it would form on the surface and immediately sink to the bottom. Then more ice would form on top and sink again, layer after layer. The entire lake would freeze from the bottom up. Solid ice, all the way through. And everything living in that lake, dead, fish, plants, microorganisms, all of them would be trapped in ice with no liquid water to survive in, no refuge, no insulation. But because ice floats, it forms a protective layer on the surface. It acts like a blanket. Underneath that frozen crust, the water stays liquid. It stays just warm enough for life to endure the winter. Fish swim beneath the ice, plants hibernate, ecosystems survive. This isn't just about lakes. It's about oceans, too. Polar ice floats on the surface of the Arctic and Antarctic seas, insulating the water below and maintaining a habitable zone for marine life. If ice sank, the oceans would freeze solid from the bottom up in cold regions, and entire oceanic ecosystems would collapse. Floating ice also plays a massive role in regulating Earth's climate. Ice reflects sunlight. It's bright, it's white, and it bounces a huge amount of solar radiation back into space. This is called the albedo effect. If ice sank, we'd lose that reflective shield. The oceans would absorb more heat, temperatures would rise, and the climate would spiral out of control even faster than it already is. In short, floating ice is a lifeline. It's a thermostat. It's a survival mechanism hardwired into the physics of water itself. Now, let's get into some mind-bending stuff, because water's weirdness doesn't stop at floating ice. Did you know that water is one of the only substances that can exist in all three states, solid, liquid, and gas, at normal Earth temperatures? Most materials are locked into one phase under everyday conditions. But water? Water is flexible. It's dynamic. It transforms constantly. And that's because of hydrogen bonding again. Here's another one. Hot water can freeze faster than cold water under certain conditions. This is called the Mpemba effect, named after a Tanzanian student who observed it in the 1960s. Scientists still debate exactly why this happens, but it likely has to do with how hydrogen bonds reorganize at different temperatures. Water is full of surprises. And how about this? Ice isn't just one thing. There are at least 18 different crystalline forms of ice, depending on temperature and pressure. The ice in your freezer is called ice IH, but deep in the ocean, or on distant moons, you might find ice 2, ice 3, and ice 6, all with different molecular structures. Some forms of ice are denser than water and do sink. But on Earth, under normal conditions, we get the floaty kind, the life-saving kind. Oh, and one more. Ever wonder why ice cubes sometimes have that cloudy center? That's trapped air and impurities. Pure ice, frozen slowly, is crystal clear. But when water freezes quickly, dissolved gases get trapped inside, creating that foggy look. Fancy ice makers freeze water from the outside in, pushing impurities toward the center where they can be removed. That's how you get those perfectly clear ice spheres in fancy cocktails. So here we are, the weird reason ice floats, hydrogen bonding. Those tiny fleeting attractions between water molecules that force ice into an open hexagonal structure. It's a quirk of chemistry, a fluke of physics, but it's also the reason life survived ice ages. The reason lakes don't freeze solid, the reason polar ecosystems exist, the reason you can enjoy that cold drink without thinking twice about the molecular miracle happening in your glass. Water is strange. It breaks the rules. And thank goodness it does, because without this one odd behavior, Earth would be a frozen, lifeless rock. Nature doesn't always make sense at first glance. But when you dig deeper, when you look at the science, you realize that the weird stuff, that's often the most important stuff, the universe runs on quirks and exceptions and tiny molecules holding hands just right. And that's pretty amazing when you think about it. If you enjoyed learning why ice floats and want more science stories that make you see the world differently, hit that like button, drop a comment with your favorite weird science fact, and subscribe for more. Thanks for watching, and I'll see you in the next one.